I imagine you are getting tired of all these receptor-receptor interactions and heterocomplexes, but they do represent a novel principle. And of course, in this lecture, we will focus on the potential impact of the receptor-receptor interactions in A2A, D2 heteroreceptor complexes on Parkinson's disease and its treatment. And there are lots of D2 heteroreceptor complexes in the brain. So, I mean, what we will do then, we will just focus as a starter of the workshop, and then you'll come up and tell me after the lecture what is wrong and what is potentially good and how the future should be in the field, and if they are of relevance or not. And here it is the one we will be talking about today then. And we'll leave the other guys for the moment. And nevertheless, I will come back to that. We will not. I should not speak so long anyhow. Let's see now. And then another complications is, of course, when you want to understand then the potential impact of A2A pharmacology on this D2 on this heteroreceptor complex. The specificity is not so great because in addition you have a lot of other A2A heteroreceptor complexes illustrated over here. This is the global GPCR heterodimer network by Borotto Escuela et al. And you can see here that these A2A protomer have a lot of connections with other GPCRs forming heterodimers. And this means, of course, that it is much more complex than we thought in the beginning. And this means, of course, difficulties interpreting the results. So there you see it, and we should be aware of that. And it all started, this project, already in 1974. Yes? Well, sorry, I did not get it. Yes, here. And continued in 1976, where we in this work we did demonstrate that, that caffeine and theophyllamine could enhance the actions at supersensitive dopamine receptors in the hemi-Parkinsonian model developed by Urban Ungerstedt in the early 70s. And this, of course, indicated at this time we did not even know that theophyllamine and caffeine were actually mainly blocking the adenosine receptors, and actually they blocked both adenosine A1 and A2A receptors. But then in '76 we got indications that in fact that is the most likely explanation for their actions. So that was in the very beginning, and now we know that we have in the plasma membranes a strong antagonistic interaction at the recognition level with the reduction of the affinity of the high affinity agonist D2 state. And you have the Brett technique, and you have the hyperbolic curve demonstrating the Brett signal coming up. And so it seems to be that all the early work and on this receptor-receptor interaction takes place in such a complex. Then we have over the years been very interested in the interface, and here you have the interface making it possible for them to interact, involving transmembrane domains, involving the electrostatic receptor-receptor interactions, especially the arginine-rich intracellular loop 3 of the D2 receptor, which then can interact with the negatively charged C-terminal of the A2A receptors, where you have especially the phosphorylated serine plays an important role, as illustrated in Borot Escuelas et al.'s work. And we also, together with Tarakanov, introduced the theory that pro-triplet amino acid homologies can be part of the receptor interface based on bioinformatic work. And here Tarakanov had introduced a mathematical approach that made it possible for us, based on 48 pairs of receptors that form or not form heteromer sets of triplet amino acid homologies that may participate in the receptor interface. They give a kind of code which determine whether or not the receptors may or may not form heterodimers. And here you have 4 sets of homologies indicated in blue in the D2 receptors and in red in the A2A receptors. And you see they may be participating in the interface, and our hypothesis is that they really are adhesive guides. And while instead the hotspots, the class, are produced via the electrostatic receptor-receptor interactions. And the human dimension is indicated here, and this is the receptor after radiography, and you can see dramatic changes here, much stronger than in the membrane preparations. Perhaps potentially they are there are more intact complexes here. The adapted protein can exert a stronger action and facilitate the receptor-receptor interaction between the 2 protomers. And here you see the reduction of affinity also in the D2 receptor, also in the human striatum. And you can see that here is the human striatum. This is controlled with the CGS. You have more left because there is a reduced affinity, so more labeling remains. And then there are lots of behavioral data in models, rodent models of Parkinsonian, of the Parkinson's disease. And you can then here demonstrate that the A2A antagonist can beautifully enhance the locomotor activity in a dose-dependent manner using a sub-threshold dose of L-DOPA. This is just an example. It illustrates that that this can elegantly be explained by the existence of an A2A-D2 heteroreceptor complex, which can, in a relevant way, participate in mediating the actions and be targeted by the A2A antagonist. And the most well-known antagonist today, and which was actually introduced in Japan, so it is actually a drug, is tradephelin. And this is then actually the whole field started based on our work especially in 1991 of the demonstration of these antagonistic receptor-receptor interactions in the dorsal striatopyramidal GABA pathway. And then here it is. Something that we should be aware of, and that Kjell recently prepared for our paper in Europe Psychopharmacology, and that you have a balance then between the homomers, A2A, A2A, D2, D2, and here you have with the adapted protein in the basal state, the heterodimer indicated. Of course, the stoichiometry in the brain, we don't know if it's trimers or if it's heteromers or what it is. And we should be aware of that. The knowledge in the field is still limited. And in the co-activated state, you get the antagonistic interaction, and as the signaling, it seems as if then there is a removal of the G protein, the GIO, because the conformational change favor instead of recruitment to the D2 receptor of beta-arrestin. So it's a rather strong antagonistic interaction coming up there. And again, we would like to emphasize that in this global heterodimer network of protomers interacting with each other and forming, in this case, heterodimers, we have to be aware that both the D2 receptors and the A2A receptors indicated in yellow here, they form lots of heteroreceptor complexes. And A2A-D2 is just one of them. And they have their own network of interactions. And these black ones, a protomer, can interact with both of the A2A and the D2 receptors, so they can then form higher order heteroreceptor complexes over there. And then, well, again, the balance is important. And I think there is so little we know today about the location of these heteroreceptor complexes, which are the major other interacting complexes. And we have the isoreceptor A2A complexes, we have other types of D2 complexes. So what we would like to know for the future is, which complexes here are located in the same neuron? And in that neuron, which ones are co-located in the same synapse and peri or extrasynaptic region? Because then you can start to play and interpret and understand the things. And we don't know that. And which are located in the same neuron but at different places, etc. So we don't know that much, and there's a lot of things to be done. And as I indicated before, we don't know very much about the stoichiometries. We indicate them here just as an heterodimer. We don't really know which is the most frequent complex formed. And of course, they have an impact, these complexes, on the firing of the striatopallidal GABA neurons. And not only do they inhibit GIO via the alpha subunit, via the beta gamma subunit, they can activate PLC, protein phosphatase 2B, and they can, in that way, inhibit the calcium channel, the L-type voltage-dependent calcium channels can become inhibited by the D2. And this firing can very strongly be antagonized by A2A, because when you add NMDA, you induce firing like this, because you depolarize the plateau potential, and then you add the D2 agonist, and then you stop it, because you suppress this depolarization with the D2. And then when you add the A2A agonist, you restore it, because you reverse this, this action, and you restore the signaling here. So they are relevant, not just for the, they have a clear-cut relevance for the firing of these striatopallidal GABA neurons, which mediates motor inhibition, as you know. And the only way we can study them in the brain in a good way at the moment is through the proximity ligation assay, which you know about, because Daciel, who is an expert in this, really showed it yesterday. Here I just want to show that they are located all over the striatum. You see the blobs? You can quantitate them very nicely per nucleus, per sample field, all over the dorsal striatum and the accumbens, etc. And here they are, and they do exist there. They are present there. They certainly would have to play a role there, being also so frequent and widespread, and so this was very important. And this was actually, we just validated this, because the original study demonstrating these complexes with PLA was by Janic's group with Tituliev. So they should get all the credit for it. We just validated it and are going to go on understanding these complexes and their regulation through this technology, actually introduced, developed in Sweden. So, when talking about the A2A receptors and treatment of Parkinson's disease, we should be aware of one thing that also I think Daciel mentioned yesterday. The chaperone sigma-1 receptor has really the same distribution pattern as the A2AD receptor heteroreceptor complex. And they are in the accumbens shell, dorsal part, especially in the core dorsal part. It's a very, and they are all over the straight and diffusely, especially high densities here. That the density of these red spheres indicate the density of the PLA blobs and the density of these complexes in the various regions. And accumbens have especially a high density in certain regions of the accumbens. There's no doubt about that. So we have to be aware of the fact that probably there exist in the CNS also A2A to sigma-1 complexes. And we are particularly interested in that because it seems as if very low concentrations of cocaine, independent of the dopamine transporter blockade, can really enhance the signaling over the D2 receptor. This is cellular models using Krebs-luciferase reporter gene assay. And with D2 alone, nothing happens with Quimperol action, and when adding cocaine doesn't do then very much. So it seems to be cocaine have a special affinity for these sigma-1 complexes. Nevertheless, even in the presence in the cells of all these three receptors together, probably forming, although we haven't demonstrated it yet, a heterotrimeric complex, there is a beautiful counteraction of the D2 signaling, even in the presence of Quimperol. As you can see over here, it's a very, very strong counteraction still developing, and in spite of the fact that cocaine is activating it and enhancing the signaling, it is really counteracted beautifully by A2A agonists. And we talk about the A2AD2, and all the time we forget about the fact that we also have A2AD3 receptor complexes in the accumbens, in the ventral, in the subcortical limbic region as well. And we also have A2D4 receptor complexes, especially within the islands or the striosomes by Graybill. And so we have to be aware that we can never be too cautious when interpreting the findings, and that these complexes probably have a interesting but still the detailed knowledge of it is still not known. And in the beginning, we actually neglected that the antagonists used in models of Parkinson's disease and in the clinic, they are not so selected by just for the A2A-beta. Of course, they also block the A2A homodimer or homomeric complex in the central nervous system. And we became aware of the importance of this balance in a long time ago. Well, not so long, perhaps. Maybe we started in 2006. But the fact is that we never could understand why could these A2A antagonists improve locomotion but not enhance this kinesia? It didn't make any sense to us. So how could that be? Because you know D2 agonists, right? They produce antitremor, locomotor activity, but at the same time they also enhance this kinesia. So why was that? And I couldn't explain it just on focusing on this A2A receptor heteromeric. It didn't make it possible. And this work was made originally by Chase with regard to this fact that A2A antagonists actually could really, if anything, reduce this kinesia, not certainly not enhance enhance them. And our interpretation was that you have this balance. You give L-DOPA treatment, and of course, with the chronic L-DOPA treatment, you get a downregulation of D2 receptors in the heterodimer, in the hormone bearers, and at the same time, when you activate D2, you always also have multiple mechanisms for it to activate phosphocret formation. And thus, there is a typical motif in the A2A promoter, so you can then increase A2A receptor formation, which will then increase the formation of A2A receptor homodimer, and instead D2 is internalizing and certainly broken down. Some of them are not quickly recruited back into the membrane. So this means that you move into a state of a change of balance, where the A2 homodimer, and also, of course, there are still the heterodimer there. These are less of them. So in this state, of course, if you can block also the homodimer with the A2A antagonists, you can start to find an explanation for these effects in the clinic and in the models of Parkinson's disease, why dyskinesia are not worsened but rather reduced by the combined treatment. And the reason in our mind could be that this signaling of A2 homodimers and A2A signaling in general operates over the PKA system. You activate then DART32, a protein phosphatase 1 inhibitor. You enhance protein phosphorylation that can have a major impact on the complexes here in the plasma membrane, because you know protein phosphorylation sites are present, we believe, in some interfaces and in the receptors themselves, change then the balance of the complexes, change their signaling, and of course there is also transcriptional activation of a number of proteins that can like adaptive proteins. So things change, and you can have a stabilization of pathological receptor mosaics that can lead to abnormal firing, will lead to abnormal motor programs, and the appearance of dyskinesias. So that was our explanation why of this story. We have to consider the homomers as well, and potentially, of course, other A2A heteroreceptor complexes, which we just demonstrated. So this was the ideas we had, and they seem to still make sense. And so when we talk about targets for A2A antagonists in Parkinson's disease, we should not just consider the A2-D2 heteroreceptor complexes in the striatal GABA neurons, but also the mono-homodimers as well as a significant target, because you see that this could special relevance for the antidyskinetic actions that appear to be developed. And of course, when you keep treating for years L-DOPA D2 agonists, of course, this change of balance, this reorganization of the complexes in the membrane will also help us to understand the wearing off phenomena that you always get with L-DOPA treatment in particular. This means that after some time these complexes will no able really to respond properly because the D2 signaling, receptor signaling in the complexes is not an operation, it's becoming a break on these complexes, and you have to move into, and you fail. The treatment doesn't work so well anymore. And we also postulated that perhaps A2A antagonists should be given early and be continued as Parkinson's disease progresses. And the reason for that suggestion you will find over here, working on the Park mouse model developed by Lars Olsson's group in our department, which is a progressive Parkinson in the mice with respiratory chain deficient dopamine neurons, and a conditional knockout mice with disruption of the gene for mitochondrial transcription factor A in dopamine neurons. It's selectively produced in dopamine neurons because you use the dopamine transporter promoter. And you have here a display of the gradual development of this motor dysfunction. And we used in our studies an MSX3, which is a prodrug of the water-soluble antagonist MSX2 with a high selectivity for A2A receptors. And what happened? Well, we were really not ready for these results, but they come out anyhow. And that is that you go on then study locomotion during 8 weeks of daily treatment, the SALIAN, the antagonist of L-DOPA, or 2 doses of L-DOPA. And when you look at spontaneous activity, that is 24 hours after the last treatment, you can see that the best one to maintain spontaneous locomotor activity was MSX3 alone. 2, 4, 5, 8, they still keep performing excellently. L-DOPA didn't do anything, didn't help at all, just keep going down. And the combination was not just as good. And here there are not any real changes between the treatments. And I think for us then, it meant for us that potentially then, to explain these results, why do we get these results with the A2A antagonist by itself then? It could be as you keep treating, things happen. It reorganizes in the membrane and elsewhere also, of course. And it leads to a problem of organization. You can move into by irreversible processes in the membrane. And that is our hypothesis. And then that could be what's going on. In spite of a lot of beautiful data in Parkinson's disease models in animals, we were really never really impressed by the data obtained in the clinic so far. And we still don't really understand why. Why didn't the A2A antagonists have a better action? And these are reviews recently from Pina Morelli, from Pina here. And they just demonstrate that there is a little reduction of off time, no worsening of dyskinesia, and an increase of on time, but rather modest actions, and not as impressive as we thought we would have, because we thought we would have the great. And the reason, of course, could be that there are many A2A receptors also in other complexes, and perhaps some of them are good and some are bad. So if we block most of them, because we don't have any selective A2A antagonist just for the heterodiner or the A2A heteroreceptor complex, we don't have such compounds around. And perhaps that can explain why we don't see as, well, there is a discrepancy. It doesn't make sense to me to have such modest actions in the clinic with these great results in animal models. Is just illustrate that you don't know enough and you are ignorant. And one possibility for an explanation, besides perhaps the most likely one, is that also there may exist here, based on the work of Flageolet and Griegard, we know that FGF-receptor-1, A2A also form a complex in the striatum, and of course if you have a A2A-D2 heteromer and the D2 doesn't get activated in Parkinson's disease, you can have a lot of important plasticity going on here, and perhaps if you block that with the A2A antagonist, you are in trouble because you don't use the potential trophic impact of FGF-receptor-1. This is just a speculation and a suggestion for you to consider. And anyhow, another aspect, but this may not be so relevant in order to understand why the A2A antagonists are not as good as we thought they would be in the treatment so far, is that, of course, in the no-go situation, in Parkinson's disease, when there are very little dopamine terminals left, of course, you all know that you have 2 two problems. There is an increase of the brake. There is, the mood inhibition system here. They will lead to an activation of the, which activates the glutamate drive onto the GABAergic neurons here in the reticulata and interna of the globus pallidus, and you get a dramatic inhibition here of the motor thalamus, so inhibiting the cerebral cortex. And I think we should consider when you move into a go situation, let's say we have a L-DOPA, then of course L-DOPA is so far the best treatment around at the present time, many feel. Although of course there are problems also with L-DOPA treatment. You can then activate D2D1 systems, you can then remove the inhibition of the striatopallid GABA neurons, you take away the brake, and you activate the movement pathway, the direct pathway that the D1 receptors is activated to inhibit this GABAergic inhibition of the thalamus, and you have a go situation with movement coming up. And but of course, with A2A antagonists, they are just modulating and the A2A antagonists are just reducing this inhibition here, modulating it, reducing it in order to restore D2 signaling a little bit here. And it doesn't really touch the movement pathway, the direct pathway is not touched. So perhaps when you only have an activation of the enhancement of the D2 signaling, the strength of the action will not be sufficiently powerful. On the other hand, D2 agonists, you all know, they are quite good in treatment of Parkinson's disease. So it may be that the modulation is not as strong as directly hitting the D2 agonists and really get a better response, as we all know we get. Although with bromocriptine or with other ergots, Pramipix or of course Ropinirol, they are all D2 agonists, right? And they do a good job, much better in a way than we've seen with A2A antagonists. So perhaps we will see in the future if we could improve and be lucky with these A2A antagonists. You will see your comments to this. And so this is more or less a repetition of what I already demonstrated to you, but we still believe that this is an interesting target for the A2A antagonist, the heteroreceptor complex, and removing inhibition, removing a brake, but perhaps it's not enough to this brake. There is some other brakes. The reorganization is more complex, so things are difficult, and it may not be sufficient just to take away this A2A inhibition and blocking out the monohormone. And then for the treatment of novel pharmacological approaches, I think you already heard about that from Daciel. And of course, the present A2A antagonists are blocking both the homomers and A2A heteroreceptor complexes like A2A-D2 and other types of A2A complexes. And I don't know if we can ever develop preferential antagonists for this A2A protomers. We will see what will happen, or preferential agonists, who knows. And the same is true also, of course, if you can develop, but that's another problem with the D2 agonists, because you know the D2, D3 are very close, so how do we get, most of the D2 agonists used today are also D3 agonists, so it's a mixture. So we hope for more selective D2, D3 agonists for the future. Anyhow, perhaps we can have more selectivity also with regard to the heteroreceptor complexes. This is just for the future, and of course, it would be very helpful, I think, to reduce side effects with these treatments. And then, as Daciel mentioned, we have the heterobivalent drugs that may be synthesized and of at least of substantial interest to have them, if they move into the brain. There are always ways to get them into the brain, I guess. With an agonist, pharmacophore, A2A antagonist, pharmacophore, and just from a principle standpoint, it will be very interesting to see with CSF injections what the anti-Parkinsonian actions they may have. And certainly they should have a high affinity for the A2A-B2 complexes as such. And then from very important for the work and for the science is, of course, and we have these small inhibitor interface peptides now, so we are breaking up these complexes and see what happens to the function and see what happened to this modulation of antagonistic allosteric communication. Is in fact this the major target for the anti-Parkinsonian action, or is it a combined action of monomers and heterodimers? That is for the future. So that is the present situation, and of course we would appreciate any comments or suggestions on this approach, the A2A antagonist approach, and if it doesn't make any sense or makes sense, or etc. So I think that's about it, and I hope I didn't speak too long now. Okay, thank you.